Hello, Math 2 Extended. This video is for Unit 7, Lesson 5. We're going to be talking about graphing square roots and cube roots. So before we start graphing these, I just want to practice evaluating these functions. So we're just going to use these two functions that I have at the top of the screen. So we've got f of x equals the square root of x plus 2, and we have the negative cube root of x minus 8. So our first example, f of 7. So if we substitute 7 in for x, we have the square root of 9, and so that is 3. F of negative 3, we're going to sub in a negative 3. We add 2. We end up with the square root of negative 1, and maybe you remember that that is I. When we're evaluating a function in order to graph it or something like that, we would just say that the function is undefined for that input. We'll talk more about that in a minute, but we have used complex numbers in the past for this graphing unit. We're not able to graph complex numbers on our xy coordinate plane, so we're just going to say that that one's undefined. And then g of 9, the cube root function over on the right side, we've got the negative cube root of 9 minus 8. This is the negative cube root of 1. And it just, if you're not familiar with how to use a cube root on your calculator, it's the button right above the square root button. But you do have to use the second function. So if you need help finding the cube root button on your calculator, let me know. But this is equal to negative 1. So f of negative 1 would be the square root of negative 1 plus 2, which is the square root of 1, which is 1. G of negative 19 is the negative cube root of negative 19 minus 8. My negative is kind of funny there. And that's the cube root, the negative cube root of negative 27. And this, when we evaluate that in our calculator, that is 3. And the last one, g of 0, negative cube root of 0 minus 8 is the negative cube root of negative 8, and this is 2. The cube root of negative 8 is negative 2, and we have this other negative also. Okay, so we're going to graph the very most basic square root function first, and then we'll graph the very most basic cube root function. So if I tried to take the square root of negative 4, I get an error. I'm going to write that as undefined. So this function is not defined for the x value negative 4. So let's sub in the next value on our table, the square root of negative 1. And the square root of negative 1 is also undefined. And let's sub in our next value. Our next x value is 0. The square root of 0 is 0, so that one was defined. So we have a point right at the origin. The square root of 1 is well defined. The square root of 1 is 1. So we have the point 1, 1. And the next value in our table, it skipped over to 4. Maybe you can see why I skipped over to 4, but the square root of 4 is 2. That's why I skipped over to 4. And then the last one on our table, we're going to input 9. Square root of 9 is 3. So this is the shape of my graph. Oops. There we go. The domain of this function, if we're thinking about this function from left to right, the domain is from 0 to infinity. The range of this function is also from 0 to infinity. For the domain, the 0 to infinity that we're thinking about is this one. For range, the 0 to infinity that we're thinking about is this one. So this function only exists in that first quadrant. You might notice, maybe you noticed, that this shape is very closely related to a parabola. It's it's half of a parabola, but it's half of a sideways parabola. So it has, and we'll talk more about the pattern in a minute, or maybe we'll talk about it right now. It does a 1-3-5 pattern, but it's a sideways 1-3-5 pattern instead. And we'll talk about how to stretch that and stuff in a few minutes. Okay, most basic cube root functions. So we're thinking about evaluating these numbers in the cube root function. So if I sub in -8 and type that into my calculator, I don't get an error like I did with a square root. I get -2. This point I can't plot on my coordinate plane because my coordinate plane only goes over to -4. And I sub in the next number, and I get the cube root of -1 is -1. So we go through this point here. My next x value in my table is 0. Cube root of 0 is 0, so we do go through the origin. The next x value is 1, and the cube root of 1 is 1. So this is almost looking like a line with those 3 points. And the last one I'm going to substitute in is 8, and the cube root of 8 is 2. So not a line. Okay, so we had this other point. I'm going to kind of eyeball-ish where it goes, maybe not that far, maybe like here. The shape of this is somewhat similar to the shape of a square root. So I'm going to flash back to that square root for a minute, where it kind of goes up and over. So we do have that happening on a cube root. It's going up and over, but then it does the sort of backwards side of that as well. It goes down and back. So it makes this little swoosh in the middle. It's definitely not a flat line right there. It's a little inflection. It kind of, switches, a little fun thing. So the domain of this is -infinity to +infinity. Cube root does not have a domain restriction. It covers all real numbers. The range is also from -infinity to +infinity. These things, cube roots, they grow very slowly, so it's just not going up very fast, but it is going up, and it does continue to go up. The farther to the right you go, the higher that function is. It eventually gets to infinity if you go far enough to the right. Okay, here's the 2 patterns that we can use for these functions. So we talked about that this square root pattern is a lot like the parabola pattern. It's just a sideways parabola. So we go up 1 over 1, up 1 over 3, up 1 over 5. The pattern for a cube root is to go up 1 over 1, up 1 over 7, and then we go down and back. Down 1, back 1, down 1, back 7. So we talked about where the 1-3-5 comes from before. I'm going to write it out again just so you can see. Whoops, 2 squared. And our 1-3-5 pattern comes from the way that squares grow up. So this, in this case, will be over 1, over 3, over 5, over 7, if we could fit it. So if we think about the same thing with powers of 3, and let's see, starting with 0, 0 to the third, 1 to the third, 2 to the third, 3 to the third. The way that cube roots grow sideways is a 1 and a 7. So we could use a table of functions like we did at first to graph these, but it's not quick to use a table of values. You've got to do a lot of calculator work or mental work. A faster way to graph is to inspect the equation and use these patterns to help us graph. So these 2 graphs have a lot in common. They both have a starting point that we will find. The starting point of the square root kind of literally is a starting point. For the cube root, it gives you this center point. And then we have to remember with the cube root to also do the back side of it. The sign changes that happen like with the h are the same as with squaring functions like quadratics and for absolute value functions and for circles, really. And then we don't have a sign change with the k of the y value of the starting point. So let's try graphing a couple of these. So our first one is the square root of x plus 3 plus 2. So our starting point is going to be at negative 3, 2. And then the stretch here is just 1. So we're going to go up 1 over 1, up 1 over 3, up 1 over 5. So that's our pattern, and we'll just graph that. The domain of this function from left to right is from negative 3 to infinity for the domain. For the range, we're thinking of the lowest value to the highest value, so it'll be from negative 2 to infinity. Okay, here's our first function where we have a stretch happening. So I'm going to go back to my previous screen really quickly. The stretch that we do for functions is always in the vertical direction. So in this case, the over 1, over 3, over 5, and the over 1 and over 7, those aren't going to change. We're always going to have those. What is going to change is that we might not go up 1. We might go up 2 each time if the stretch factor is 2. Or we might go up 3 each time. Or if our stretch factor is negative, if we have a reflection, instead of going up 1, we might go down 1 each time. So it's the vertical part of the pattern that we're changing and stretching, not the horizontal part. So we'll always use a 1, 3, 5 sideways for these square root functions. So another unique thing that this function has is that it's started with the constant. Instead of having the plus 2 or the plus 1 at the end, it has shown up at the beginning of the function. And that sometimes happens, especially when you have a negative stretch. It's not that uncommon. If it helps you, you can scribble it out and add it over to the end. So our starting point is negative 4, 1, which is right here. And our stretch is negative 2. That means we're going to go down 2 each time for our pattern. So we're going to go down 2 over 1. And our 1, 3, 5 isn't going to change. So down 2 over 1, down 2 over 3, down 2 over 5. So we've kind of reflected this this square root, and we've stretched it so that it's a lot kind of taller than they have been on the last one. The domain of this one is from negative 4 to infinity. We read that from left to right. For the range, we read it from the bottom to top. So this will be negative infinity up to a high value of 1. So those are square roots. Let's try some cube roots now. So this cube root has a starting point of 2, 3. Because it's a cube root, it's going to do the 1, 7 pattern. And the stretch is just a 1. So let's mark that starting point, 2, 3. And sometimes the 1 and the 7, or sometimes the 7 doesn't even fit. I'm going to kind of eyeball it just to help me get the shape right. So I went up 1 over 1, up 1 over 7. Now I'm going down 1, down 1, back, 7. And those points should help you get sort of that basic shape. And when I'm drawing these, I don't usually draw them from left to right. They usually look not great when you draw them from left to right. I usually start at the center and go up and over and then down and back. And usually you get a little bit better shape if you do it that way. So our domain and our range are both all real numbers. Let's try one more cube root graph. So the starting point of this cube root graph is 0, 1. The stretch is a negative 3, so we're going to go down 3 to start, but our pattern is to go over 1 and then over 7, just like before. We don't change the sideways here. So we're going down 3 over 1, down 3 over 7. That puts me at 8. And now, because this one went down and over. Whoa, I missed. This one's going to go up and back. So this is going to go up 3 over 1, up 3 over 7. So this one is very stretched. The domain and range of this one are actually kind of easier to see because it has that stretch to it. Okay, so now we're going to try going backwards. If we have the graph of the function, can we write its equation? So I want you to focus on the starting point of the square root graph. This one starts at the point 4, 2. And so our function is going to look like, and you should check the stretch as well. This is a 1, 3, 5 sideways, so we don't have any stretch that we need to notate. So the function is equal to the square root of x minus 4 plus 2. Sometimes the starting points on a cube root can be a little bit tricky to see. I would mark them and kind of see if you can see that rotational symmetry of the two sides. So this one's negative 4, positive 2. Again, the stretch this is doing a pattern of 1, 7, so we don't need a stretch to it. So let's see, I'm just going to use y this time. So this will be a cube root. I know it's a cube root because it's got both of the sides to it instead of just having the right side. So this will be the cube root of x plus 4 plus 2. Okay, our last graph right here has a starting point of 2, negative 1, and the stretch is that it's going down 2 over 1, down 2 over 3. So our function is going to be, and by the way, the y here, it's random. You can use either. So f of x is equal to negative 2 square root x minus 2 minus 1. Okay, here's a little word problem, sort of. We've got an amusement park ride called a rotor. Maybe you've seen similar things, maybe not, I don't know. It spins you around, and when it gets to the right speed, the floor drops, so you're just kind of suspended against the floor, and that centripetal force is like just keeping you like pinned to the wall, almost like you're lying down on it. So we've got an equation right here for this. The speed necessary to keep the person pinned to the wall is related to the radius. So for a larger sort of cylindrical room, you need a faster speed. And the smaller the room is, the slower the speed is needed. So we want to graph this. So the R is kind of like our X and the S is our Y. So let's just maybe make a little table. And so let's think about, well, 0, 0. We don't, if our room is 0 size, we don't need any speed to our spin. If the room is 1 meter, our output is 5 times the square root of 1, so that would be 5. So the next one is 5 times the square root of, and I could pick 2 here, but then I'm going to get some kind of weird decimal answer. So I'm going to go ahead all the way over to 4. 5 times the square root of 4 is 10. So 4, 10. And if I'm being smart, I'm going to pick 9 as my last input. So 5 times the square root of 9 is 5 times 3. That's 15. 9 and 15. So we can kind of sketch this. Okay, so this axis is telling me about how large the radius is, and this axis is telling me about the speed. The speed is in meters per second, and the radius is in meters. Okay, so use the graph to estimate the radius of a rotor that spins at a speed of 8 meters per second. So if it's 8 meters per second, it looks to me like that would be about 2.5 meters. Okay, 2.5 meters is about, I don't know, 10 or 12 feet. I might have said that wrong. Maybe it's not 10 feet. Haha, I don't know. Okay, the last little thing I want to talk about is revisiting average rate of change. We talked about average rate of change before. Average rate of change is if you averaged the slope of the function over a specific interval, and we found it using the endpoints of that interval, of the function on that interval. So average rate of change is always specific to a particular interval. So the average rate of change between 0 and 2, we're talking about this. We're talking about this slice of the coordinate plane, and so we're talking about that slice of the function. And so if I just am thinking about that slice of the function, the average rate of change would be that it's going up 2 over 2. And 2 over 2 is the same as 1. Our next interval is from 2 to 7. So again, we're talking about x values here. This is an interval. So we're talking about this interval from 2 to 7. So when we think about that interval, here's where the function starts on that interval. Here's where it ends. It's going up 2 over 5. And that fraction doesn't reduce. So we would say the average rate of change is 2/5. And then our last average rate of change over there at the bottom, it's for the entire interval from 0 to 7. And so for that interval, we would use this starting point, let's see here, and the ending point is here, and we would think that it's about how it's going up 4 over 7. So it definitely grows faster between 0 and 2 than it does between 2 and 7. All right. We might not always have a nice graph from which to count the average rate of change. So I was using the grid to just figure out the slope. But we don't need a graph in order to figure out average rate of change. We can calculate average rate of change using the slope formula because average rate of change is just a type of slope. It's just an averaged slope. So we might have to do it from the function instead of from the graph. This generally means we're going to have to calculate our y values. So our question is, what is the average rate of change of the function f of x equals the square root of x minus 3 over the interval from 4 to 19? Now remember, these are both x values. So for both of those, we need to calculate the y value. So f of 4 is the square root of 4 minus 3. That's the same as the square root of 1, and that's 1. So what we're saying is that this function goes through the point 4, 1. F of 19 is the square root of 19 minus 3. That's the square root of 16, which is 4. So our graph also goes through the point, oh, careful. Our x value is 19 and our y value is 4. So we had to calculate our y values in order to figure out the average rate of change. So the average rate of change for this function on the interval from 4 to 19 is, we would take our y values and subtract them and divide by the difference of our x values. So this is 3 over 15. That's an average rate of change of 1/5. So if you're doing average rate of change from a function instead of a graph, calculate your y values and then use the slope formula. All right, our last little follow-up question is, what is the domain of the function? So sometimes we don't have a graph and we might want to know about the domain. Well, in that case, you want to think about like what errors you might get from that function. And for a square root function, we can't take the square root of negative numbers unless we are, of course, going into the complex number system. But when we're talking about functions and graphing, we can't take the square root of a negative number. So what we need in order for this function to be defined is we need this number, x minus 3, we need that to be greater than 0. We need it to be positive. And so if we solve this little inequality, we get that x has to be greater than 3. And that's the domain. We could write it, whoops, I should use a bracket. It can equal 0 for a square root because the square root of 0 is 0. So minus 3 has to be greater than or equal to 0, which means x is greater than or equal to 3. So our domain is from 3 to infinity. So this is the domain in interval notation. This is the domain in inequality notation. Okay, the last thing is in class we just did a comparison activity. So for the video, I'm going to skip that. It would be good maybe to practice some average rate of change on some of those functions, but that's it. Test is coming up, so let me know if you have any questions or need help with anything. Thank you.